G'day, welcome back to our discussion of inverse functions. In the previous video lecture, we talked about when an inverse function may exist, what functions in fact would have an inverse. And in fact, we found that many functions aren't going to have an inverse because they are not one-to-one. One-to-one was that idea that we discovered that captured the idea of when an inverse function would exist. So we said a function was one-to-one if every number in the range, so you can see this yellow line here is a fixed number in the range, right? It's a fixed y value. So every number in the range corresponds to exactly one number in the domain. In this case, it doesn't correspond to exactly one number in the domain. It corresponds, in fact, to many numbers in the domain. There are many numbers in the domain of this purple function that produce the single yellow y value that I've got here. And so this function is not one-to-one. And so our conclusion in the previous discussion was that that function will also not have an inverse. On the other hand, if you have a function which is strictly increasing, like this function, then it will have an inverse because each value in the range will correspond to precisely one x value. So no matter which y value you choose, there will be precisely one x value that produces that y. In other words, horizontal lines only cross the function once. One-to-one functions have horizontal lines only crossing the function once. And so this one will have an inverse. The function on the right will have an inverse, the one on the left will not. And if you think about what functions will be one-to-one, they have to be either increasing everywhere or decreasing everywhere. If they have these kind of maximums and minimums, then you're going to be able to find multiple points that have the same y value. And so they won't be one-to-one. That leads us to say that a function has an inverse if and only if that function is one-to-one. So let's think about a function that takes elements from its domain and maps them to the range. So I'm going to call the domain this set with elements capital X. And so I'm going to put these bars to show that's a capital, and the set capital Y is the range, the codomain, but essentially the range. So this function maps elements from the domain here, this set capital X, into the range over here, this set capital Y. Well, an inverse function is precisely a function that undoes that work. So it takes elements from the range of F and maps them back into the domain of F. So here is our inverse function. And if we say more, in fact, if we say that, in fact, f of x equals y, then if f inverse is undoing that, then when I put y into f inverse, I have to get x back, because that's precisely what this picture represents. And so these equations entirely define what we mean by an inverse function. So putting that a bit more formally, what we're saying is if f is a one-to-one function, that's absolutely required, and we take an element from the domain of f, let's call it the point x, and it produces the point y, that's what this picture is representing, then the inverse function satisfies, well, when you plug y into it, it reproduces x. So it undoes the work of f. So it essentially completes this loop. F takes us from the domain into the range, and then f inverse takes us from, well, the range of f back into the domain of f. And so we call this function the inverse, or I'll just usually say f inverse. The symbol for it looks like that's a -1 power, but in fact this should be pronounced as f inverse. And these two together define what we mean by an inverse function. So these ideas entirely define what we mean by an inverse function. This simple equation and then the picture that goes with it that sort of describes what we mean by this mapping by a function and its inverse can be summarized in theorem 2.81, and we see the domain of f inverse. Well, f inverse must take the elements that are in this set y, and that set y is simply the range of f. And f inverse, on the other hand, produces elements over here in the set x, and that set x is actually the domain of the original function f. So in other words, when we build the inverse function, what we do is swap the domain and range of f. So if we want to know the domain and range of f inverse, it's just swapped from the domain and range of f. We'll do an example of that in a sec. This third quality here, this table is just from the book, is precisely what we've got written over here, just in a slightly different order. The inverse function's one-to-one. There's only an inverse if the function was one-to-one to begin with, and the inverse undoes the work of the function, so the inverse must be the inverse of itself. So if I undo the inverse, I get back to doing the function. In other words, if I take this value y and produce this value x, by using the inverse function. What undoes that work? Well, the answer is this trip, and that is just the function f. So that's expressed here. The inverse of the inverse is back to the original function. And there's only one inverse. It's unique. Okay, so that summarizes kind of the properties of the inverse function. Let's look at some more specific examples. So here's a specific function. Let's find the inverse at least at a point. So if I were to calculate, let's say, f of 2 for this function, then what we're going to get is 2 plus 2 in the numerator, and the denominator we're going to get 2 lots of 2 minus 1. So that looks like 4/5 to me. And so what we're saying is f of 2 is equal to 4/5. So if we plug 2 into the function, we get 4/5 out. If this function has an inverse, so if this function is 1-to-1, and the argument I'm going to make relies on this function being 1-to-1, but if it is 1-to-1, then we can calculate f inverse of a certain value. F inverse of what value? Well, we plugged the value 2 in to the function, and we got the value 4/5 out. So if we plug 4/5 into the inverse function, it should produce 2. And this is precisely the idea that we've got expressed up here more generally, but for this specific example, this is what this expression is telling us. If f of x is y, then f inverse of y is x. Well, we know f of 2 is 4/5, so f inverse of 4/5 must be 2. Let's actually go further. Let's calculate the inverse of the f of, let's say, 2 in this case. I know what f of 2 is. We just calculated. F of 2 was 4/5. So I can just plug that in. F of 2 was 4/5. This is the composition of functions, right? It's f inverse composed with f. So this becomes f inverse of 4/5. And f inverse of 4/5, we just said, was 2. I could do that the other way around. Let's take the composition of f with f inverse. So in this case, I know f inverse of 4/5. That's the only point we've bothered working out here. So f inverse of 4/5, we said that was 2. F of 2 was 4/5. Okay, so we've gone around in a complete loop in both cases. And on this figure, that's exactly what it represents. If I start at 2, apply the function, let's think about this equation. If I start at 2, apply the function f, start at 2, apply the function f, I end up over here at 4/5. I then take that 4/5, apply the inverse function, and that takes me back to 2. In other words, we do a complete loop back to the original point. The same with this expression, except here we're starting at 4/5. So we're starting over here, and we're plugging that into the inverse function, which takes us to 2. And then we're taking f of 2, and that takes us back to 4/5. So we do a complete loop in this case, in the second equation, but that loop is clockwise. In the first equation, we started here, and we went clockwise, but starting at 2. All right, so these are examples, or this is an example of what's known as the cancellation equations. The previous example shows us that if we take a value out of the domain of f, let's say, this is the value x, plug it into the function, we produce something in the range, and then we plug that value into the inverse function, it takes us back to where we started. So regardless of what x is, f inverse of f of x has to equal x. That's exactly what we saw in the previous example. In that case, we used 2. And going through that loop, we found the 2 came back. And so this is true, in fact, for all x. But that x has to be in the domain of the original function. We're doing a composition of functions here. So we're putting f of x, we're composing it with f inverse. And so this value x has to be at the very least, in the domain of f for that composition to make sense. And similarly, in the previous example, we saw that we could also go the other way around. F of f inverse of x. We start over here in this case. We're calling it x instead of y, but that's just a symbol. We're starting with an element that can be plugged into f inverse. And if I can plug it into f inverse, I must be starting in f inverse's domain, which you remember is the domain of f inverse, or otherwise known as the range of f. And in this case, we'll also produce that same number because we calculate f inverse of x, it takes us from here over to there. We plug that into the function f, that takes us back to where we started. But where we started was the domain of f inverse, so x better be in that domain. So these together are known as the cancellation equations because you can see that as long as you start with elements in the appropriate domain, the equations essentially cancel each other out and we end up with the original value x back. So So let's do a bit of an example. If we just take a straightforward example, let's say we take the function f of x is equal to 3x. If I just draw a quick graph of that, that's a line through the origin. Let's pretend it went through the origin that has slope 3. And so that must be a one-to-one function. So I don't need to necessarily calculate it every time, but we can see this is a one-to-one function. No matter what y value we choose, the x value, there's only one x value that corresponds to that y value. And so we can find the inverse function. Well, just working intuitively, if my function f creates values by multiplying by 3, how am I going to undo that action? What would undo the idea of multiplying a value by 3? Well, the answer, I hope you see, is that we would divide it by 3. That will give us the inverse function. And then we can check. Let's check, for example, on the value, let's plug in 4. So let's calculate f of 4. So f of 4 is just 3 lots of 4, that's 12. And the idea is then we take 12 and put that in the inverse function, and we should get 12 over 3, which is 4. And this behaves exactly like we would expect. F of 4 gives us 12, that means f inverse of 12 must give us 4 back. So that is the right inverse function. It does intuitively what we expect. It undoes the work of the original function. So we can apply these cancellation equations here, and we can calculate for every value of x, f of f inverse of x, which in this case, f inverse was x over 3, and then we can calculate f of that, which is 3 lots of it, and so that produces x again. And that's exactly what the cancellation equations tell us should happen. We can go the other way around and plug f in first. So f of x is 3x. The inverse of that, well, you take it and you divide it by 3, and that again gives us x. And that's demonstrating exactly what these cancellation equations up here are telling us. And in fact, we can use the cancellation equations to work out how to find inverses more generally. Let's do an example where we use that cancellation equation to actually find the inverse function. So we have here a function, f of x is 4 plus the square root of x. I want to use the cancellation equation that we talked about earlier to find the inverse function. And notice that f of f inverse is going to equal x. So from that cancellation equation, f of f inverse, what is f inverse? Well, I can just plug that into the function, right? Because here's the function. So f of f inverse is, well, the function f is the function that takes 4 plus the square root of whatever you give it, and what I'm giving it is the inverse function. And I know that has to equal x. And so I can solve that. This says the square root of f inverse of x is just x minus 4. And so I can square both sides, and I find that f inverse of x is equal to x minus 4 all squared. And so there's the inverse function. So we use the cancellation equation to calculate that inverse function, which is pretty neat. But we're going to do it in general in a slightly sort of more simplified way. But before we do that, let's talk about the domain and range here. Let's talk about the domain of f. The domain of f, in this case, looking at this function, the domain is all the non-negative numbers, so 0 to infinity. And the range of f, well, if you sketched a graph of this function, you would find that it is the square root function, which has a range of 0 to infinity, but it's been moved up 4. So it looks something like this. So here's a graph of our function f of x, and that means that the range of this function is 4 to infinity, all the possible y values. So what's the domain of f inverse? And what's the range of f inverse? Well, what we found before was essentially we just swap them. So the range of f inverse, the values we can plug in, are the ones that come out of f. So 4 to infinity. And the range is 0 to infinity. So we can find the domain and range just using what we know about that original function, f. So let's add to the graph a sketch of the inverse function. And the inverse you can see here is just a quadratic, and the vertex of this quadratic is at the point 4, 0. And so I put the point here somewhere, 4, 0, and the domain is all the values greater than or equal to 4, so we're only looking at the left-hand side of that quadratic. And so it's going to be looking something like this. So here's our inverse function, and when you compare it with the original function, f of x, and compare it with f inverse of x, hopefully you can be convinced that that graph can be obtained by reflecting it through the line y equals x. This is not the best graph in the world, but this is an important statement about functions and their inverses. And it's always going to be true. The graph of inverse, or the graph of f inverse, can always be found by reflecting y equals f of x through the line y equals x. So I'm taking this and I'm reflecting it through this line. So I'm taking each of these points and I'm reflecting it across the line, and we're always going to find that the inverse function is the reflection of the original function. And as we saw before, f inverse is the inverse of f inverse is the original function. So I can go the other way, and I can find f, if I know f inverse's graphs, by just reflecting it through the line y equals x. So let's look at how we might go about calculating inverse functions more directly. So I'm going to redo the calculation on the previous page and just show you how, in general, we can work this out. If we start with the function 4 plus the square root of x, then I'm just going to call it y, right? And look, that's what we've got here. 4 plus the square root of x, and here I had something complicated under there, but I'm just going to write this as 4 plus the square root of x, and then I'm going to swap x and y. And if you look at our previous calculation, what I did at every point past here, what I did was begin to solve for this complicated thing underneath the square root. So what I'm going to do is call it y and then solve for it. Right? So I'm going to write down the original function. I'm going to swap x and y, and then I'm going to solve for, in this case, solve for y. And so we're going to end up with square root of y is equal to x minus 4. And then we're going to square both sides to get y. And what we're left with is precisely what we had in the previous exercise, which is the inverse function. So if we follow this algorithm, set y equals f of x, swap x and y, and then solve for y, we'll end up with the inverse function. And so this is our set of steps to find the inverse function. Let's do another example. So let's solve for the inverse of this function. And so all we do is call the function y. So set y equals 2 over 5 minus 3x in this case. I'm going to swap x and y. So we're going to end up with x equals 2 over 5 minus 3y. And then we just have to solve for y. So to do that, I'm going to multiply the denominator across and then do all of the things we need to do to solve this equation for y. And we'll end up with 3xy here. And on the other side, we get 2. And we're solving for y. So in the end, what we end up with is, just if you'll excuse the algebra done quickly in my head, we end up with something like that. So there's the y we went in search of, and that means that the inverse function, that's not just any old y, that's the inverse function we were looking for. And you could rewrite that, in this case, as 5/3 minus 2 over 3x. But there is our inverse function. We can check whether this is reasonable by checking a point. Let's say we looked at f of 1/3. Plugging that in the function, we get 2 over, and in the denominator this is 5 minus 1, so it's 2 over 4, which is otherwise known as 1/2. In other words, f of 1/3 equals 1/2, and if this is the correct inverse, then we expect f inverse of 1/2 to produce 1/3. That has to be the case. And so we can check that by plugging a half in here. And so if I plugged 1/2 in here, we can say this is 5/3 minus, well, this is 2 over 3 times 1/2, and this is the same as 5/3 minus, and that becomes 4/3, and what we're left with is 1/3. And so, in fact, the relationship we expect for an inverse function is satisfied here. And so we know, or at least we have some good beliefs that this is in fact the correct inverse function, and I haven't made a mistake. All right, so have a go at the post-video exercises, and I will talk to you shortly.